Good morning, everybody. My name is Elmar Bartlmae. I'm moderating today's session. It's the final virtual conference of the ETEKINA project, which has been running now for 53 months. So we have one more month to go, and I'm really happy that we have here now, a nice set of presentation lined up today. Just a couple of housekeeping things. We are recording this session so that people who have registered to this event, they will also get a link to it afterwards. This will take a couple of days until we, have it all ready and transformed into the right format. If you have questions, that's also, please ask questions when you have them. But we would like you to use the chat to do that. And we also like you to mute the microphone if you're not, unless you really have to talk. We have a session towards the end where we also can have a kind of a joint discussion. So then we can also have maybe open the floor a bit further. And yes, I'm here, and my colleague Corinna, she will look after the chat so that we make sure that we're not missing any of your questions, because it's always sometimes a bit difficult to follow everything on different screens and so on. So that's really here from my side. I mean, initially we had planned to do a live conference, actually a face-to-face conference at Brunel University. Unfortunately, we had to change this because of the COVID situation. Now it's a virtual event, let's make the best out of this situation. I think it's going to be very interesting, especially what the 3 demo cases will say and what we will learn about the technology. And so I now will give the floor to Nerea and Nieto, who is the coordinator from IKERLAN, and Sam Jouhara, who is the technical coordinator of the ETEKINA project from Brunel University.
Okay, thank you. Thank you very much, Elmar, and thank you to all of you that are attending today this conference on behalf of all the project partners. We are really glad to share with all of you the results we have obtained during the last years. So we have organized a conference according to the agenda you can see there in the screen. And well, maybe not to be late, and in order to be on a schedule, we can just move to the first presentation. So I will share now my screen. Okay. So well, we will give you an overview of the ETEKINA project, the challenges and outcomes for energy-intensive industries. Well, I will first take you some years back in order to understand which was the context when ETEKINA was created. We will review the project objectives, the main challenges and outcomes, apart from the success stories you will later hear about. And then Professor Hussam Jouhara will introduce the heat pipe technology and its implementation in industrial processes. So,
super.
Sorry, I think maybe somebody has the microphone unmuted. Well, I will go on. As you all may know, energy-intensive industries in Europe are characterized by very high energy production costs, as well as by an important level of CO2 emissions. Energy production costs effectively account for up to 40% of total production costs in soft energy-intensive industries, while emissions represent a quarter of total European CO2 emissions. This is also the case of three of the process industry sectors involved in ETEKINA, which belong to the non-ferrous metals, steel and ceramics sectors. Although a substantial resource efficiency improvement has already been achieved in these industries over the past years, energy and fuels still represent a significant part of the production costs. This makes them suffer from a lack of competitiveness on the world stage, since energy in Europe is expensive. We are all aware of the increasing energy prices we are facing right now and the impact on energy-intensive industries, which further confirms that energy is a crucial element for the competitiveness of our industry. A way for gaining significant energy savings, together with substantial greenhouse gas emission reductions, is the use of waste heat recovery systems. The waste heat recovery market was projected to reach around 50,000 million euros in the last years. Europe dominates this market, although it's also expected that the Asia-Pacific region will experience the highest growth rate in the next years. So for these projections to materialize, and for the European manufacturing and user industry to benefit from these developments, further technological breakthroughs were still needed at the time when ETEKINA was launched. And these breakthroughs were expected to improve the energy efficiency of heat recovery equipment and to reduce the installed costs. So this was the context in which the ETEKINA project was created, and which motivated all of us to join forces in a consortium in order to demonstrate that recovering more than 40% of the waste heat stream in energy-intensive industries is possible. For that, we established the following objective for the project: improving the energy performance of industrial processes. And for this to be possible, the valorization of waste heat by heat pipe-based heat exchangers has been addressed within the project. The solution has been implemented in 3 industrial processes, as we will see later, demonstrating its economical feasibility and therefore its market potential. Although the main focus of heat recovery solutions should be on the environmental and energy savings benefits, it's true that their implementation will depend primarily on the economics and the perceived technical risks. So industrial manufacturing facilities will invest in heat recovery only when it results in savings that give a reasonable payback period and the perceived risks are negligible. So therefore, minimizing economic costs of heat pipe-based heat exchangers has been or was a very important target during the design phase. Although you will hear about 3 success stories today, the path has not always been easy, and we have had to address different challenges within the project. With regard to waste heat recovery opportunities, although there is a significant percentage of industrial energy inputs lost as waste heat, there is a lack of information on the source of the largest waste heat losses in different sectors and processes and the nature of different waste heat sources. So knowledge of these factors is critical in determining the feasibility and extent of opportunity for waste heat recovery. In ETEKINA, we used a bottom-up approach to evaluate waste heat quantity, quality, and recovery technology barriers in the 3 industrial applications representative of the non-ferrous metals, steel, and ceramics sectors. Numerical models were used to characterize different physical phenomena involved in the processes, as well as in the connecting piping in a multivariable basis, such as fluid dynamics of air streams and burned gases. Numerical models, like the one shown in this slide, were also used to characterize different physical phenomena involved in the heat exchange among the different components of the receiver process and the recovered heat. So in this example here, you can see a model corresponding to the process of Fagor Ederlan. As you will see later, in this case, the waste heat of the fumes of one furnace is transferred into another furnace through a heat pipe-based heat exchanger. So this model allowed us to understand the dynamics expected in this heat transfer and also served us to define the control strategy for the heat recovery system. Although you can also only see here some black boxes for the furnaces and for the heat pipe-based heat exchanger, there are also specific models behind each of them. So you can see here, for example, the model corresponding to the heat pipe heat exchanger, which was previously designed by Brunel and Econotherm for Fagor Ederlan. Another challenge related to waste heat recovery opportunities is the lack of demonstration projects. Although technologies for waste heat recovery exist, their operation still needs to be demonstrated in different industrial sectors in order to ensure their wide deployment. So in ETEKINA, we have demonstrated the feasibility of heat pipe-based heat exchangers for 3 different industrial sectors. And in addition, we have developed a tool for the analysis of the replicability of this technology in other industrial sectors. The tool provides a first approach of the potential savings that could be achieved using heat recovery technologies based on heat pipe heat exchangers at different sectors. However, it's worth mentioning that in case the results were positive, a posterior detailed engineering design would always be needed before going through the real implementation. And finally, before going to the introduction of the heat pipe technology itself, you can see here a list of challenges we have to face related to the waste heat recovery technology. These are common challenges in industrial processes and include dealing with high temperature, with corrosive or fouling exhausts, and multiple heat sinks requirements, developing a cost-effective waste heat recovery technology, facilitating the concept of energy export from the recovered heat to enhance the business case of the developed systems, working with certification bodies, for example, for high-pressure system designs. This was a requirement for one of the use cases, as you will see later. And the most important thing, we need to ensure that the systems installed are invisible to the process. That means that they save energy without having any negative impact on the process. So in order to address all these challenges, a modeling-based design of the heat pipe-based heat exchangers based on both theoretical and numerical models was carried out to allow specific challenges for each of the 3 applications to be considered. New designs were generated and optimized using a combination of not only theoretical models, but also laboratory testing. Brunel University also developed a methodology for using the waste heat recovery system based on the industry type and the required heat sinks. So to sum up this part, an integrated approach to process innovation has been proposed within a ETEKINA project covering design, simulation, operating conditions, and process management, together with a breakthrough technology for waste heat recovery. And now I give the floor to Professor Sam Jouhara.
Sam, you're muted.
Thank you very much, Nerea. Can you see my screen? Okay, thank you. Thank you, Nerea, for the introduction and the details about our journey so far. So, as you heard from Nerea, it has been a journey. We had to go through various complex procedures dealing with real industries, applications. So that puts kind of responsibility on us as developers to ensure what we do is like you heard right at the end, whatever we design is invisible to the process. While it benefits from energy recovery, it doesn't add any complications to the process, so the companies basically don't see it. But we've been talking about the heat pipes. Many of you are aware of the technology, but just in case, I will just go through it quickly. Heat pipe technology, a heat pipe is a tube. If you look at it from outside, simple tube, nothing complex. But if you are to cut through this tube, basically it has a saturated environment, small amount of working fluid in an enclosure that is hermetically sealed. The heat is transferred from the heated section to the cooled section through latent heat transfer. So, for example, when you, in this case here, you absorb the heat in the evaporator section, this heat is absorbed by the working fluid to change phase from liquid to vapor. The vapor will go to where the cold surface is and condenses on it to give out this latent heat. Once that is done, it changes phase back to liquid, and then gravity brings it back to the reservoir at the bottom, so it can do the cycle again. If gravity is not on our side, then we have to use other forms like capillary or centrifuge to bring this liquid back. But in our project in ETEKINA, we don't use wicks. Basically, we use gravity-assisted heat pipes, or as you call thermosiphons. Here's an example. If you are to hold one of these heat pipes in your hand, put it in a kettle. What you notice here is basically from the kettle to the hand, the temperature is quite uniform because inside the tube itself, the working fluid is saturated, but the surface goes cooler as you get near to your hand, as your hand is now absorbing the heat. And the temperature is not an issue based on the combination between the shell and the working fluid. What you see here is a sodium heat pipe that can go above 1000 degrees. So it all depends on the application, the temperature, and then once that is done, then based on the thermal design, we get the final design approved and manufactured. From thermal point of view, the heat pipe heat exchanger, like you see in this illustration here, is a number of heat exchangers linked thermally in parallel. So each heat pipe is a heat exchanger in its own right, and linked with the adjacent ones through a parallel link when we take the Ohm analogy, the Ohm law analogy. So basically, this is how the thermal design is developed, and if in real life, this is what you see. And the configuration here is really based on the thermal design itself. Each one of us will have at least one heat pipe. If you happen to break your laptop or you just take it apart, you should see at least one. So these are copper heat pipes here. They have a wick inside because with the laptops, they move sometimes against gravity, but it's a heat pipe nevertheless. It transfers the heat in a passive manner from the heat source, in this case, the CPU or the graphic card, to where space is available so you can absorb the heat. There are so many advantages of the heat pipe technology, hence its application in ETEKINA. Multiple redundancies, as I said before, each heat pipe is a heat exchanger in its own right. So basically, if a number of these heat pipes are to go out of action for any reason, the remaining heat exchangers will continue operating until the next maintenance cycle. We can manage the fouling. In ETEKINA, we use CFD to help us in the design, so we ensure the particles in the exhaust are suspended as the exhaust go through the heat exchanger, so we don't clog the system. For that, we also allowed ease of cleaning in case fouling builds up. So that is also something that is integrated in the design itself. And like you saw before, there are no cold spots in the hot region, which means we don't have any cold spots that corrosive elements will condense on, which is a common issue in conventional heat exchangers. Like I said before, when I showed the sodium heat pipes, based on the design, based on the environment, we designed the system to have compatible materials so don't interact or don't get corroded as we proceed with the actual application. The heat pipe itself can have water as a working fluid while receiving heat from exhaust above 1000 degrees. It is the case because the temperature of the heat pipe inside it is actually somewhere between the hot source temperature and the cold source temperature. So if we can cool the heat pipe quickly enough, we can reduce its temperature to manage higher heat transfer rate. And the scale of that can go from few watts, like an electronics management, to a few megawatts, like we have one system of 12.6 megawatts installed. So scaling it up or down is not an issue as the thermal design allows. For those of you who happen to have done an experiment on the heat pipe, it's extremely reactive. So that is one of the biggest advantages of it, which takes me to the most interesting and useful element of its characteristics, which is the passive operation. We don't need to force a fluid through the heat pipe to transfer the heat from the hot source to the cold source. Like you saw in the illustration before, the whole process is done in a passive manner, which gives the heat pipe technology an edge in certain industries. In the ETEKINA project, what you see here is really an example of a development we have done where we actually take the case from A to Z. So this is an example of an integration where we actually do everything in a virtual manner before we do the actual installation. The process we followed in ETEKINA started with identification of the actual potential heat recovery in the process. We've done that as a consortium. Once that is done, we define the technical specifications for the implementation. We've gone through energy auditing, installing sensors, collecting crucial data. Once that is done, we had everything, and we included everything in something called data capture form, which included, in addition to the thermal data, the characteristics of the heat sinks, the characteristics of the heat source from all chemical composition point of view. Once all of that is done, the heat pipe theoretical and mechanical design was conducted in close collaboration between Brunel University and Econotherm UK Limited, which manufactured these systems. And In parallel to that, we worked with the demo cases and the RTDs to develop and finalize the P&ID, the piping and instrumentation diagram. This is a crucial element for any design as it puts together everything required for the demonstration. Once that is done, then we know what the installation looks like. Then we transform the P&ID to an actual 3D installation. The 3D installation should look 100% the same as that in real life once approved. So once the demo case is happy with it from dimensions point of view, locations point of view, instrumentations point of view, then the implementation and commissioning is concluded. And the commissioning for all the ETEKINA units was conducted under the supervision of Jonathan and Brunel to ensure the design data was achieved. So this is really the roadmap for the implementation in ETEKINA, and in any waste heat recovery application really it can also be applied to. This is an illustration for the heat pipe unit. And the heat pipe units have been applied in various industries before, but what you should actually see is it does have a physical separation between the heat source and the heat sink, which gives us physical separation between the two streams, minimizing, in certain scenarios, eliminating the possibility of any cross-contamination between the two streams, which is also another advantage. And these heat pipes can also just absorb the heat from one side and put them on the other side. Just to give you an idea about the partners who have actually allowed the demonstration, also partners in the ETEKINA project, without going too much into details because that is coming later. We have 3 industries in our consortium. The aluminium industry, which demonstrated in Fagor, Ederlan in very close collaboration with Insertec with regards to the oven operation. And the concept there, like you see it here, is to recover heat to heat gas that will be used in the furnace. And we set ourselves a target of 43%. And the challenge for us there was really designing a heat exchanger that will react to a very complex control system that is required for the oven operation while providing air at 316 degrees back to the furnace. So we had to deal with high temperatures, multi-stage heat exchanging process, and that was done and concluded. And you can see here from the 3D, the actual 3D installation, the photo of the real installation, and the commissioning date where we achieved the design data that was done late last year. The second industry is the steel industry in Slovenia. Our partners there are Ravne, the very, very close support from Joseph Stefan Institute. And the target there was to do 2 things, really. One, to recover the heat for a typical application gas, combustion gas preheating. In addition, they have a potential for energy export, a local district heating network. So the challenge there was really the energy balance between the energy going to the preheating of the gas and that exported beyond the plant itself, and how that balance is done through a very robust control system. So energy reuse and energy export, quite a challenging design actually it was, because the temperature of the exhaust can vary, sometimes 200 degrees up and down. So that was a very big challenge. We had to work very closely with the partners on the design of the system, and pleased to say that we managed it with various complications that were made possible thanks to the collaboration of the partners in Slovenia. You can see here the air preheater section and the exhaust leaving going into the water section where the energy is exported. The last installation was in the ceramic industry. We've been successful in the ceramic industry before, but this one here has certain challenges in Atlas Concorde. The challenge here is the high temperature for the water, coupled with quite a challenging exhaust conditions that we had to deal with, and large units. We're talking about 700 kilowatts units, and my colleague from Atlas Concorde will expand on that later. The minimum target for our recovery was 41%, and I'm glad to say that we have achieved that nicely. This is the scale of the system during the commissioning, and I thank every partner involved in these demo cases on behalf of the consortium. It's been a real pleasure working with all of you on these successful demonstrations, and thank you.
Well, okay, thank you very much, Nerea. Thank you very much, Jouhara, on this introductory element of this conference. I think amazingly we are still on time. This is excellent news. So I would say let's just continue quickly on our success stories, and we will start off with our demo case 1, the steel production process of that was the heat pipe heat exchanger with the two sectors that were installed at Metal Ravne. And so may I ask Kristijan Plesnik, he is the energy manager, to share now his presentation and make himself heard, seen. Is he actually online? Yes, you are. Yes. Okay, good.
Hello from Metal Ravne. See you my presentation.
Yes, but we don't see it in the. It's not in the presentation mode yet.
Do you see now?
Yes. Now we see. Yes. Yeah.
Today we present demo case 2. Here is our table of connection, condition description, monitoring results will be presented by colleague Fuad, and next steps. The first, I present some data about our owner. Metal Ravne is member of C group. We cover the entire steel production chain, from the collection of steel scrap to the sale our finished products. Key indicator revenue is around 700 million, EBITDA is around 40 million, and quantity around more than 450,000 tons per year. Here you can see data about Metal Ravne. We have more than 200 quality grades, around 400 years tradition in steel making. We have own research and development department, around 1,000 employees. Our sales per year is around 80,000 tons, revenue 200 million, and we invest about between 15 to 20 million per year. We have niche production, very worldwide sales network, and we present more than 50 countries. Our market, around 70% we have in the market in Europe Union, and about 16% about United States of America. We are one of the 3 largest manufacturers of steel tools in Europe. Here we can see about our heat recovery system. We used T2 sink. One is for heat, for air heat, and another is for the water. This combustion air we used in our walking beam furnace, and hot water we used for warming our working place. Heat recovery is more than 47%. Here we can see how we integrated our heat pipe heat exchanger into our production system. This system working in the bypass, and in this solution we can anytime switch off the system and don't have any impact to our furnace. Our heat pipe heat exchanger has been in operation from the end of October, with new stops due to the maintenance test and plant production stop. In this period, we produced more than 1,000 megawatts hour, around 60% combustion air and around 40% hot water. Before I talking about 2 sections of heat pipe heat exchanger, we used air and water. Of course, we have a very high challenge to optimize the air exchanger, because in the situation, if we have low consumption of combustion air, and this time the temperature in the heat exchanger go up, and then we problem with working in our system. This way we make a good solution. We included one flap for mixing the air, and now we continuously reaching a temperature between 330 to 360 degrees. What care can be. Hello, do you hear me?
Yes, now.
Oh, thank you.
Okay. Hello, I am Fouad Al-Mansouri, coming from Joseph Stefan Institute in Slovenia. Now I will present a result of the operation heat pipe heat exchanger on, I will take this characteristic for one working, normal working day from in 6th of January to 2022. Now the first the temperature diagram that the exhaust temperature from the furnaces rang or come out from vary from more than 150 degrees to more than 475. Also, like before, my colleague is go that we mixed this exhaust and to provide a stable inlet temperature for the air section of the heat pipe heat exchanger. Can you see that in the grow line in the about 350 degrees of this in the diagram? The other side, this exhaust temperature of the also decrease to about 250 degrees in the air section of the heat pipe exchanger, and also to about 180 degrees in water section, and finally realized to the ambient. Next, please. Now can we see this? Now this temperature of the in the water section of the heat pipe heat exchanger. The temperature diagram for the water, following temperature, exhaust temperature, inlet about that we speak about 250, 240, 205. That the blow line in the diagram, and they left this section about 180. That the brown line in this diagram. In the condenser part of the heat pipe exchanger, inlet temperature of water about 50 to 55 degrees, and left about 70 degrees depending of the weather during the day. Between the night and day here about 5 degrees. Now we see that the system, district heating system, it was maybe more optimized to lower temperature of water than in the before on at the start of the not operation, but this project. Now this diagram, can we see the diagram of flow rate of the exhaust? Exhaust from the furnaces that in the lower part of the diagram, that gray line, can you see? And front of them, that's the diagram of the air combustion. After addition of air, can we see in the top of this diagram the flow rate of exhaust at the inlet of the air section of the heat pipe exchanger. Meanwhile, that the flow rate of water, it was in the maximum all time about 7,000 kilogram per hour. That the blow line in the middle. Next, please. The other also characteristic, can we see the heat recovery power, that the temperature at corresponding heat recovery power for the air section of the heat exchanger. The unit to scale that quantity on the diagram are lined in degrees and kilowatt. The average power for the air section that vary, can we see, about 200 kilowatt. The increase of temperature combustion air that from about 30, that inlet temperature inlet of air combustion about 33 degrees, and increase to 200, about 200 degrees after lift the air section. That's what we contribute to energy in the system. Next, please. Here we have the temperature and the corresponding heat recovery power from the water section of the heat pipe exchanger. This unit scaled the quantity on the diagram below are also aligned in degrees and kilowatt Celsius, degrees Celsius. Here can we see that the power at the below at the top, that about 130 to 37 kilowatt hour were in working day, and also temperature increase from more than 50 degrees to about 70 degrees when they left the condenser part of the heat pipe exchanger. Next, please. Now, some of about the power, exhaust power that in this reference or first primary stream, which can we did the in orange or dark orange at the higher diagram, can we see in the that in the yellow diagram that in the total power heat recovery power from the both section. And can we see that we achieve about 33 kilowatt hour in the heat pipe for both section. In this time we have about 500 kilowatt this reference or that from furnaces the exhaust, the power of exhaust when we potential, we can speak of potential. The efficiency, it was more than 60% in this time, but when we go speak about the more than about 50% that on for whole year. But between working both section, the efficiency is higher. Next, please. Now we it was this depending of the energy from the recovered heat is calculated also the energy saving in both section, depending of the flow rate of in temperature for air combustion, for exhaust, and for temperature of water for heating. The weekly difference, can we see that in working week, that in week period, for this period, observed period biweekly, that about 570 megawatt hour the energy recovered, heat recovered from this heat pipe heat exchanger. And normally that you can see 35 megawatt hour from the air section and about 22 megawatt hour heat recovery from per week for in water section. Next, please. Now, with the economic impact and saving, we calculated this for this period from 5 of November 2021 to 30 January 2022. Can we see that this amount is about in megawatt hour total of more than 532 megawatt hour in both section, and amounted by about more than 30,000 euros, depending of the, here I use the prices in last year, it was lower. Now the prices of natural gas is more than double for the company in Slovenia, for industrial company. And this time we also we have reduced the CO2 emission by 63 ton CO2 during the observed period, and that also amount about more than 5,000 euros. And this time also we don't and this don't include the CO2 emission. In Slovenia we have in average the emission CO2 emission by megawatt thermal power from district heating about 0.37 ton per CO2 per megawatt hour. And if we calculated this, our contribution of the heat for heating system, that about 73 ton CO2 emission. This reduction also for the district heating, if we consider the Slovenian average. Next, please. This next we have on some prediction the yearly heat recovery, which is calculated also on the average heat saving in the period of when taken in really working in this previous time. And what can we see? That we achieve more than 2,400 megawatt hour heat recovery for both, and also reduce for that also reduce the consumption of natural gas for about 177 more than 1,077,000 cubic meter natural gas, which is a reduction of CO2 emission by 330 more than 330 ton CO2. The estimation, this economic estimation impact here about less, more about the 200,000 per year. This very, very, I think, economic, efficient economic effect impact of this system. The next, please. Now, if we take in consideration this prediction expected economic saving, and also the investment as it was in our project, can we see that the investment return of investment more less than 10 months for this investment, and this very I think very economic efficient, and due to reduction of demand for water for heating purposes for district heating CO2, can we also emission reduced by 270 or 280 ton CO2 per year. The energy saving and the economic impacts are even more significant than anticipated, with the energy saving and the economic saving impact are even more significant than anticipated. With increasing prices of energy and emission allowances, the economic impact will be even higher. This my part. Please, Kristijan, the next, and finish the next step.
Thank you. Before we're talking about potential to optimization, and we have this field on the water section side on the pipe heat exchanger, where the capacity of the flow could be increased due to the high temperature of the exhaust. But in this period, we well acquainted with the heat pipe heat exchanger system. We today know how it responds, and this way we sure that we will use it on another our aggregates. This is for our side.
Well, thank you very much, Kristijan. Thank you very much, Fuad, for this overview on your demo site. I mean, very impressive figures we saw there. I don't know if there are any questions there on the chat yet. No, nothing I can see. So I would then say we would. Oh, there's somebody. Shanda, if you just want to type in your question in the chat, I think that would be That's kind of the way how we try to do these things. And then I'm going to very quickly move on. I mean, this is very impressive. I mean, the figures, just a very quick question maybe I have, Fuad. You gave us the numbers, and obviously we saw a huge rise in energy costs over the last months. What month did you, I mean, what was your kind of date or data? Where does it come from? Was it kind of October, September, October, when you made these calculations on the energy costs?
The energy cost in this prediction for 2022. And I take this, I put this cost for this newsly cost from this year.
Okay.
But when I calculated the economic effect for the period of working, I take both, that the prices for in December, November, and also in January, these different prices. But this is the last for yearly calculation that I take in consideration the price in 2022.
Okay. Good. I don't know that there's no question coming in on the chat. So
sorry, Elmar. Can we allow Chanda to give his question without the text, if that's okay?
Yes, let's do that. Chanda, if you want to.
Without text. It's price without tax.
I have a question with the Dr. Jouhara.
Hello, Chanda. How are you?
And Dr. Jouhara, this is Chanda Kamra. And
hello, Chanda.
You have given your references.
Thank you.
I had been in the ceramic industry last 35 years. So I am more interested in how many projects you did in the ceramic industry. Right. Just send your email ID so that I can send my data and other my requirement.
Perfect. Thank you very much, Chanda. Please send the email and I will reply accordingly. Thank you.
Fine, sir. Fine, sir.
Okay, and we will come to the ceramics in a moment, but first let's move now to Spain, where we have Ederlan Gonzalez from Fagor Ederlan presenting, I think together with Nacho Yebra from Insertec on the demo case 1, as we call it in ETEKINA. We had those 3 numbers, and that was about the aluminium foundry at Fagor Ederlan. So if you can share your presentation.
Yes.
And
1 minute. Can you see it?
Yes.
Okay. So this is Eva Gonzalez from Fagor Ederlan, and with me is Nacho Yebra, who is from Insertec. And Insertec is a supplier of Fagor Ederlan, and they have involved in the project with us. So we will explain the ETEKINA HPHE changes in the aluminium front. We're going to see first a Fagor Ederlan overview a little bit, a general description of the process, the ETEKINA HPHE changer for Fagor Ederlan, which is the demo case, and in the fourth place we will be preliminary results and the conclusion in the fifth point from a research and development project to an industrial project, what we have learned. About Fagor Ederlan overview, let's say that Fagor is a cooperative group which is part of corporation Mondragon Corporation Group, which is the biggest cooperative group in the world. We are a global automotive suppliers, and we manufacture components for passenger cars, but also for commercial and industrial vehicles. We are always innovation. There is no other solution for us, and in order to achieve the market technological challenges. Our sales, just a little figures for you to understand which we are. Our sales last year was a little bit lower than normal because of the COVID situation, but was 540 millions. The components we manufactured about 50 million units, and we are leaders in the 4 technologies for aluminium and irons, which are low pressure die casting, high pressure die casting, gravity, and machining. And about employees, we are 4,000 employees, more or less. 72 of us are cooperative members. We have 70 foundries around the world. In Spain are the headquarters and several foundries, but also we have Mexico, Brazil, Slovakia, and China. We are a tier 1 for automotive, so we are in contact with the main OEMs, and our main clients are BMW, Renault, Nissan, Daimler, and Stellantis, among others. And just to finalize, we manufacture components in chassis like brake discs, knuckles, calipers, and also for the powertrain, engines, and so on, electric powertrain and structural, and for commercial and industrial vehicles, powertrain components, and engines, and transmission, clutch, and steering components. Okay. So move on to the general description of the process where the demo case was installed. It was the demo case is developed in a low it was for the manufacturing of aluminium knuckles. The aluminium knuckles are components that very important in the car, are part of the security of the car because they join the brake system with the direction with the steering. So they cannot break, and they are very demanding. The mechanical characteristics are very, very important. We start with aluminium ingots, and it has, let's say, to summarize, 4 phases. The first one is melting. After that, we molding the part. After molding the part, we need a thermal treatment. This is important in order to achieve the mechanical characteristics. And finally, we machining this component. Each phase has its own steps. Here, in this figure, the steps which are in red color are the ones which need most energy in order to complete it. Of course, we are talking about the melting. The melting is the steps where more energy is needed. But in the melting step, we've been working, let's say, forever. In order to save energy and to use it in different kinds of users. For us, it was a challenge to work in the thermal treatment where we didn't find any possible solution, and it's also very demanding phase because the thermal treatment is very long in a time. Right. The other steps in green doesn't need too much heat, and the blue colors means that we need to cool the parts. So the ETEKINA hyperheat exchanger for Ederlan was in the thermal treatment, and the objective was to recuperate energy from the first furnace, the solubilized furnace, which is a 540 degrees centigrade, and use it for the second furnace, for the iron furnace, which is a 165 degrees centigrade. Here, a picture of the furnace itself. This is important, the operation modes. I will do like this, if you don't mind. Well, this is the mode when the HPHE exchanger is not working, when there was no demo case in this project. This is the first oven with the fumes that with the energy go out of the process. The second furnace is the same. The fumes with the heat go out. This is a mode. A preheating operation is not very important. Just to mention that there is this mode. The important mode is here. Here is when is recovering energy and how is working from the first oven. The fumes are collected and goes through the HPHE exchanges that keeps this heat, so the fumes go out with another temperature. In the second oven, in the second furnace, the fumes goes to this HPHE exchanger and take and capture the heat left there, and goes out with higher temperature and go again to the oven. The last mode operation is just a functional one, because just when we have too much heat in this oven, right, it's just a bypass in order not to capture more energy for this oven. So the fumes in this case go out without passing through the HPHE exchanger. This is some picture. It's already, I think, Sam has shown some pictures. This is the HPHE exchanger. It was necessary to put a platform because there was not too much space for the demo case. And here we can see the oven and the connections. Another detail of the HPHE exchanger. And about the preliminary results, well, here we can see the temperatures of the two ovens. This one, the first one, 450, and the second one, 165, as was predicted, and it was constantly in the period of monitoring, which is from October to January. Here, yes, a stop because of Christmas vacation. We can say that the fumes for the first oven enter to the HPHE exchanger at 400 degrees. We have to dilute something because there was too much high. The temperature was too high for this for the HPHE exchanger. So the fumes enter with this temperature and go out with about 220. So this heat is already in the system, keep in the system. If we go to the second furnace, we can see that the fumes goes out at about 197 degrees centigrade, a little bit higher than we expected. And when they go to the HPHE exchangers, capture all the heat that was or keep it, and so the fumes go out from the HPHE exchanger at 300, and that's the fumes that enter again to the oven, to the second oven. Here, just the pipes, the water pipes and the oil pipes. Of course, the oil pipes are able to keep more temperature and more heat, of course, and they work constantly. They work all right during all the monitoring period. The flow rates from the primary and secondary ovens work a little bit different, but this doesn't interfere in the working of the system. And we can say from the primary stream that the heat recovery power was 80 kilowatts, and it was maintained for all the period of the monitoring time. So the heat efficiency is about 40%, and also maintained during all the period. Here we also measure the natural gas saved. At the beginning, we will measure every day how much gas, natural gas, we were consuming. As you can see, there is a lot of variability. This is one of the problems we face because making these trials in the production site what's happened is that the production is not every day the same. So the consume of gas is very related with the production. We can see here this period of time, there was no HPHE exchanger, and we can see a little bit, the consume of gas is higher. But because of this variability, this period of time, the HPHE exchanger is working, but because the variability is not very good seen. All right. So what we did, these are another way to measure, and it was to measure the accumulated gas consumption. So if you see the first period of time when the ETEKINA or the demo case was off, let's say, the accumulation is the curve is much higher than when the ETEKINA is on. When the ETEKINA is on, we can see the curve is less, and again it increased when the ETEKINA is off again. Here in this graphic you can see again the same issue. First, when the ETEKINA is off, it changes the inclination when the ETEKINA is on. And the last point is how to go from a research project to an industrial solution. Well, here we've been working in 3 different scenarios. First one is the actual demo, the demo who is already installed in Fagor Ederlan. The second scenario is how will be an HPHE exchanger, an industrial one, because we have learned a lot, but there was something that because we didn't know at the beginning, we wanted to be sure. We were very worried about not to influence the production of the part, the mechanical characteristics of the part. So there was some mistakes in orders. The diverter, the valve, the pumps were a little bit higher than needed. And the 3 scenario is the 2 scenario plus the prices of the energy and the CO2 to 2022, because it's true that from the beginning of the project, or even from last year, the prices of the energy and the emissions of CO2 are very different. So in this table, we can see we have, as we have said, the scenario 1, the 2, and the 3. And here we have calculated the energy transfer, the hours working, the gas consumed, the CO2, the power needed, the savings, and the return of investment. In the first one today, well, we have these savings, annual savings, and the return of investment is 54 months. But as we already said, If we make an industrial one and all the connection and the system change a little bit, we are sure that we can get a 40. I mean, the annual savings will be higher, and the return of investment will be less, will be 40 months. If we apply the prices in the third case, if we apply the prices of actual energy and CO2 emission, we see that the return of investments is much lower and is below 2 years. And well, for this is important because as I said at the beginning, was not easy to find an inversion for energy savings that was the return of investment was less than 2 years. Even 3 years was not easy to find. And this is all I have to say. Thank you very much. And you have my email, my contact email, and also from Insertec in case you need it. If you have any questions.
Great. Thank you very much, Yebra, on this presentation. Yes, I mean, just because you mentioned the contact details, obviously, if you know, you kind of can't remember exactly who you want to contact, you can always contact us on the ETEKINA homepage, and then we will forward that to the people who you're trying to reach. So this is always also a possibility. That's just what I'd like to mention here at this stage. Great. I don't know if there are any questions. I don't see.
Yes, Elmar, there's one question from Charles. The exhaust stream heat exchange is a logical opportunity, but there are also viable opportunities for heat recovery from the products as they are cooled between processes. That's the question.
Well, that's a good question, because we heat the parts and after we cool the parts in order to heat again. We've been studying this, but not possible. There is, for the moment, we have not found any solution to this. It will be very great for us because there are many parts cooling down, but we haven't found any solution to this problem.
Sam, do you want to add something on that?
Yes. Hello, Charles. It's a very important question. There is also one very important element. By doing that, we have to do it indirectly. We can't allow any direct contact between the stream and the product, and especially in the aluminium industry, and in particular on the aluminium recycling industry, this question always comes up. So it is crucial that we always understand the end use requirements, and in particular the requirement for physical separation between the two streams. One of them is contaminated, one of them is the actual valuable product that they're dealing with. That is a very important question nevertheless.
Great. Well, thank you very much for that question and replies. And I think we can now move on to our Italian friends. Luca Manzini from Concorde will present the ETEKINA heat pipe heat exchanger that was installed there at the ceramics production line, or next to the ceramics production line, I should say, because it's actually situated slightly outside there. I can see already the presentation. That's good. Can we hear you?
Can you see it?
I can see it and we can hear you.
Good, good. Hello, my name is Luca Manzini. I take care of energy management for ceramic at Concorde. So I'm in charge of managing the markets, the regulatory issues and normative issues about energy, and also, of course, technical issues regarding energy efficiency. When we talk about ceramic at Concorde, we talk of a large company, which is owned by Group of Concorde, a even larger company with owns several manufacturers in Italy. As for Atlas Concorde, the production is in Italy, in 3 plants, mainly in the district of Sassuolo Fiorano, so it's near Bologna, near Modena, and a production which exceeds well over 15 million square meters of tiles, floor tiles and wall tiles also per year. We work 24/7, 30 days per year, and roughly we have 800 employees, both for plant and office. A turnover of over 300 million euros per year, mainly coming from export. So our main, let's say, income come from selling abroad, which is one of the reasons for which we are aiming to such a reduction in cost, because we have a strong competition from other countries, okay, especially when it comes to raw materials and energy. Our tile size ranges from, let's say, traditional small tiles, okay, 30 by 30, and we go over 2 meters long tiles with huge slabs. Okay. Of the 3 plants, we decided to focus this project on the Fiorano plant, which is the main plant in ceramic Atlas Concorde among the 3. In it, we have 2 spray dryers, 7 dryers, 5 kilns, a natural gas cogeneration via an engine, okay, of 7 megawatt of electric power output, almost entirely consumed inside the plant. We have more than 250 workers, and the production is over 10 million square meters of tiles per year produced nowadays. What is our role in ETEKINA? Of course, we have the role of demonstrating the benefit of having such a system installed in our place. Okay. So we were involved in the work package 2, which is the process analysis. We took care of sampling of flows, which were the temperatures, and so on. We contributed to the design of the heat pipe exchanger, giving the constraint that we were able to accept. Okay. Physical dimensions, pressure losses, and so on, and providing them to the real designer manufacturer, which were Brunel and Econotherm. And we, of course, took care of installing and demonstrating the effectiveness of the system. And of course, we had to contribute to the dissemination and communication. Which were our key role? Our key role is about knowledge of the ceramic cycle, and which are the best available technology applied to the ceramics. And also our role is to know how to properly integrate innovative contribution, innovative ideas to the ceramic plant in the ceramic machinery. This is an overview of the process, of ceramic process, which could be divided into 3 main areas: the powder production, the tile production itself, and the sorting and logistic. Of course, the main 2 energy intensive processes are the first 2. And so we receive the raw materials. We carry on with grinding them into a rotating mill. We get the slip with the, which is a fluid, a mixture of water and clay. And then we spray dry them and obtain the powder. Then we go on pressing this powder into the shape of the tile, which has to be first dried, so had to be taken to almost 0% of humidity. Then has to be decorated and glazed. And then it comes the firing section, when the tile itself is cooked and becomes hard. And then we go on with squaring, and in the end, sorting, packaging, stocking, and all the logistics section. You can see here highlighted the three main areas where we have natural gas consumption, apart from the cogeneration. So our target in ETEKINA was to take advantage of some waste heat in one of these departments, and to carry this, to take advantage and carry it to another department. Okay, about thermal energy, we can have here a split of it. As you can see, over 50% of it goes into firing. Then it follows the spray drying. And then we have almost 10% of drying and a very, very small percentage of other usages. In a more, let's say, detailed representation, we've got here a Sankey diagram of how the energy demand is split among the different machinery, and how different machineries are were before ETEKINA connected. We did carry out some energy efficiency activities. I could consider them as the best available technologies and state-of-art, system. Okay, which means carrying the hot air from the kiln to the spray dryer section, and the same hot air to the drying section. We always discarded these gases, which were at an interesting level of temperature. And in this project, ETEKINA, we are going to focus on this heat stream. We want to take advantage of this and carry it to the spray dryer section. Here we have a simplified sketch of the system. So we take the heat from the stream, the exhaust gases of two ceramic kilns. We carry it to the heat exchanger, the heat pipe heat exchanger here. You see on the evaporator side, we've got the exhaust of the kiln. Then we go to the filter. And on the secondary side, we've got a closed loop of superheated water, which provides the heat to a fin coil heat exchanger, which itself warms up air to be fed to the spray dryer. The spray dryer is the machinery, you remember, at the beginning of our process, which dries up the slip, and which works at 500, 600 degrees. So it's a relevant, let's say, saving for the spray dryer to receive the same air, not at 15 degrees or 30 degrees in summer conditions, but at 120, 140 degrees. There were some challenges to be met into this project, both on the heat pipe heat exchanger side and on the heat sink side. Talking about the heat exchanger side, heat pipe heat exchanger side, there was to be a challenge in coping with the stream, because the async compound could be let's say dangerous for the heat exchanger itself. So the condensation and the particulate in the heat stream could be, let's say, something that had to be faced by the heat exchanger itself. And also, too higher temperatures were to be avoided. During the spray dryer shutdown period, heat had to be transferred directly to the filter. So that has something that had to be taken care of. And also certification issues. There were a lot of markings that had to be provided to this unit in order to be allowed, in legal terms, to be operating in our plant. And as for the heat sink side, we took care that there was a feasible interaction with the plant. Okay, so we had to check about dimension, weights, admissible pressure drops for the inlet layer to the spray dryer. Of course, we had to carry out, say, detailed analysis of safety issues that would arise when having pressurized water running at a hot temperature, superheated water running through the plant. And again, all certification issues had to be dealt with and to be dealt with effectively, because we cannot, of course, allow to have a system operating with no certification completely fulfilled. During the first year of the project, we mainly focused on identifying the correct, most suitable heat source among the kilns in the plant and the most suitable heat sink. In the second year, we focused on design of the system and the suitable heat medium, which at last was identified as water. And in the third and fourth year, the executive phase of the project took place. We started with the integration and then the demonstration, which is going on right now. Here you have a visual representation of the last 24 months. Of course, the pandemic affected somehow the progress of the project. So we had some delays due to the fact that we had to stop activity for some times. And also when we started again, also components and machineries, it was more difficult to obtain them. Let's say supply time were prolonged, so everything was more difficult. Okay, but in the end we managed in last August to carry on with the system integration and commissioning. Of course, we have some expectation on this project now that it's working. And the main one comes from containing energy bill, especially due to the fact that nowadays, say, energy market figures are really terrible, both for natural gas and for CO2, which are the two main savings that we are going to obtain via ETEKINA. We expect to recover 41% of kiln exhaust sensible heat and reach almost 4,000 megawatt hour of natural gas savings. and over 800 tons of CO2. And consequently, a relevant natural gas consumption reduction on the spray dryer. Of course, during the project phase, design phase of the project, we designed this system P and ID. Okay. And according to this, once it was, let's say, approved, we proceeded with installation. We had to find a new place for the unit, so we had to build a new building, okay, in order to accommodate the system. We had to operate on the kiln piping, okay. So the original piping, which was going straightly to the filter, had to be modified in order to accommodate the bypass, which goes to the heat exchanger, which is going to be positioned here, and then goes back to the original piping. We had to modify the fan to install the superheated water pipeline running both on the outside and on the inside of the plant. Here you see a detail of an expansion omega with expansion joints. Okay, more expansion joints in another curve of the piping. Here inside the factory. A curve to the heatsink. Here you see here a portion, a small portion of the supply drive, which is very tall. It's almost 20 meters tall. And here you've got the air intake, which is going to be preheated via this fin coil heat exchanger. Here you see the piping, the superheated water piping going in and out of the heat exchanger. As for electric system and control panel, of course, we had to provide also all the controls and logic to control temperatures, the bypass of the system, and the three-way valve in order to operate properly the water loop. You see here at last the heat pipe heat exchanger unit delivered and just integrated with the water piping. And here a picture of us in the commissioning day. As for the marking of the unit, let's say that a lot of documents had to be provided. So the unit had to undergo a lot of approvals and a lot of certificates in order to meet all the requirements that we needed here in Italy. So it had to be approved by Lloyds, okay, a third party who took care of approving the unit as a PED category 4. And it had also a CE marking and the declaration going with it. Then there were other documents to be provided on the Italian side, which we took care of. A brief representation of temperatures and let's say power over 1 week of operation. Here you can see the temperature of the streams. Okay, we are just seeing the moments when the spray dryer was working. Okay, so you see the temperature now in this week would vary from 250 degrees at the inlet of the unit to 280 degrees, and the bypass valve was almost always shut down, and the same as the three-way valve. As a consequence, we reached a power recovered of almost varying from 600 to 700 kilowatts. And let's say this was what we expected the unit to deliver, also in terms of energy saving. And you can see the proof here on the spray dryer consumption. Here you can see the first days of January, when the system was shut down because the kilns were not operating. And then the same system when the same spray dryer when the system was operating. So you see the shift, okay, in energy consumption. So as a conclusion, we could say that yes, the system design and the knowledge of normative regulatory asset issues allowed us to realize an innovative heat recovery. Innovative because it comes from a heat source which is discarded usually to atmosphere, at least here in Italy. And we consider it an important energy stream and an important solution. The natural gas saving is one-to-one with the power measured in the unit. So, for 1 kilowatt that we are saving, we are measuring on the water side, we are saving 1 kilowatt of natural gas in the spray dryer. And the savings has doubled when compared to what was 1 year ago. This to the high increase of natural gas prices and also to increase of EUA quotes, CO2 quotes in the energy market. So the return of investment of the system is under 4 years, which is something that would allow us to approve it for further, let's say, implementations in other plants. 2 more hints. The control system is crucial in this application, both on the safety side, of course, because we are dealing with a superheated water, so you don't want to pass from liquid to vapor phase, and on system performance. And last, when dealing with the stream from the kilns and with this kind of say of stream, the condensing issues and the cleaning issues are to be taken into account. The condensing issues are not avoidable when the unit is cold at the beginning. So it is something that has to be taken care of when designing the unit with the proper materials, how Brunel and Concorde did. That's all from my side.
Great, thank you very much, Luca, on your presentation. I don't know if we have we've ran up. We're slightly overrunning at the moment. I don't know if you've got any questions in the chat. I don't see any. But I mean, we will have a short discussion time anyway in the you know, at the end of this conference. So I would say we have a short. Oh, Shanda, you're raising your hand. Okay, do you want to ask a question, please?
What is the size of spray dryer? Which spray dryer is that?
It evaporates 11 tons per hour.
1,000 liters per hour.
11,000 liters per hour. Yes.
Oh, it's some sort of equal to ATM 1110. I'm right.
110.
Yeah, 1110 is equal to SACME. So as per your data, you have given the air, right? 110 to approximately it's a 50,000 kg per hour at 110 above 125 degree.
Sorry, I didn't understand.
No. For the ATM 110, we need the more than 50,000 kg of air, right?
Yes, but there is a cogeneration system operating as well.
Okay.
Okay, so part of the air is provided as so exhaust gases from the cogeneration plant.
Okay, for the kiln, you have taken the flue gas from the smoke section, preheating. No, for the input flue gases, you have taken from the preheating from smoke section of kiln.
The input flue gases, I didn't sorry.
No, the input source, the waste heat source, exhaust gas input.
I don't understand about the exhaust gas input, you said.
You have the heat recovery unit. There are two streams. One the exhaust input from where you recover the energy, right? It's the kiln from kiln.
From
right?
two kilns, yes, two kilns.
Yeah, kiln. It's from preheating smoke section, the cooling section.
No, not the cooling section. No. The cooling section is clean air. So this is something.
Okay.
Clean air is something that we are already doing. Is pretty. It's easy to deal with.
How did you deal?
The dirty kiln, the dirty part.
I agree with it. How do you deal with the contamination? Is there a lot of dust contamination? How do you deal with it?
But of course,
Is
we
there
got.
any cleaning system?
No, of course, that was one of the challenges that had to be dealt with, especially by Brunel and by Econoterm, okay, in designing the unit. Bear in mind that the unit is right after the kiln.
Okay.
So after that, anyway, we are going to the filter, because here in Italy, it's mandatory to have a filter, a back filter, before going to atmosphere. So we are going to filter anyway, okay? We would have filtered it anyway. What did we do? We tried not to have condensing in the outlet of the heat exchanger in order to avoid condensation in the filter, because that could be let's say, tricky as well, okay?
Okay, but what is the distance between your kiln and the spray dryer? How many meters in distance?
The distance?
Yes.
The distance is over 300 meters.
Oh my God, it's very good.
So yes, it was very distant. Okay, so it's a very, very long pipeline going. It's 300 going and 300 going back.
That's why you are choosing the gas to water, right?
I don't know exactly.
That's why you consider gas to water due to the long distance.
Yes, of course. But yes, but you also have to consider that we would not. We are not allowed to directly put that into another machinery. Okay, we cannot put that exhaust as such into that machinery, especially when you've got cogeneration. It became too complicated. Okay.
Okay, thank you very much.
That kind of recovery allows us to reach higher temperatures of inlet air, the spray dryer, apart from the one that is substituted from the cogeneration exhaust, of course.
Sorry, Luca, if I may interject, Chanda. I mean, what we're trying to do in this project, if I may, is to stay within the heat pipe heat exchanger section, not to interfere also with what's beyond the wall that separate the heat exchanger from the actual industry itself. As you know, Chanda, there are so many trade secrets, there are so many issues that we really don't want to disclose about this plant or other plants. I would leave that that to Luca, of course, at his discretion. So this is why, if you look at the installation, we had the installation done nearly near the outside of the factory. So we don't have any issues with confidentiality or anything like that for the process, which I believe Luca is trying in a nice way to say. So we're trying here to keep the information that is confidential. But if you have any specific questions, Chandra, please do send us an email and we'll answer what we can answer.
Okay, sir. I will do.
Thank you very much. Thank you.
Thank you.
What I said was public, so it was not a problem. Okay, at this level, of course.
Oh, sure. Thank you.
Great. Let's just also give Anna Mezukita Marti the chance to ask a question here.
Hi, hello. Okay, first of all, congratulations for the consortium, for the project, and of course for the presentations. All the speakers have been great, and it has been quite easy to follow all the demo cases. I have only one question, which I think I know the answer, but I just want to ensure that you are using, in the ceramic case, you are using the gases from the exhaust of the kilns, okay, and you are using the hot, you are using it to preheat the air used in the spray dryer, okay, but there is an intermediate step, which is the water, and my question is related with that. I think that you are using water as an intermediate fluid because of the distance between the kiln and the spray dryer. Is it right?
It is right. It is right. Let's say that it's also a more flexible medium. Okay.
Yes.
I mean, let's say going to liquid give the system more flexibility also. And this is something that I wouldn't go into further detail, actually.
No, it's not necessary. I guess that you are using a liquid because of that.
The answer is yes. I mean, another option could have been using diathermic oil. Okay.
Yes, thermal oil. Yeah.
But for safety issues, we decided to discard it. We prefer to have to deal with pressure than to deal with fire hazard.
Yeah. Okay. Yeah, this was my question. Thank you very much.
Okay, Sam, you wanted to add something?
No, I'd just like to add, I mean, Luca, amazing summary, really, but also from what Anna and Chandra have just mentioned, it is actually one of the biggest challenges we had in ETEKINA is to address the end user requirements regarding the energy transportation, the way the heat is delivered to the process, and as I said, without actually getting involved in confidential matters. So that was one key element for our research, for our consortium in general, especially that we have a relative focus consortium. So in this scenario here, what Luca mentioned, really the key element that we had to consider in this project, which are basically fire hazards, long distances for the heat sink, and also the space. The space was quite limited. So we had to take all these into account. And as you saw in the presentation that Luca just finished, the high pressure, the high temperature water actually was ideal for the process, because it made the energy transportation quite efficient, and also from space optimization point of view, it was also a success for that demo site. So thank you, Anna, thank you, Chandra, for these questions. They do highlight what we have achieved in this project for this sector. Thank you.
Okay, great. We now run out of time a little bit because we are supposed to be in the coffee break for the last 15 minutes. So I would suggest that we have a short break now, and we resume at in about 10 minutes, so maybe 5 to 12. I think that should be fine, huh? Because we already raised a couple of questions that we don't have to raise again later on. So I'll see you all hopefully in 12 minutes, so 5 to 12, and we continue then. Thank you very much. If this had been a real conference, and this would have been one of the highlights, I guess, because then you could discuss things about future projects, future collaborations, and everything. But it's so here we are virtual, so I think we can now basically continue. And in the agenda we have we thought, well, we want to look at two specific challenges that ETEKINA faced. One is on the communication, and the other one is kind of a policy issues in Europe, and I'm actually the project manager of ETEKINA on the communication side. I'm from the European Science Communication Institute, so we are the partners here. ESCI, as we say, it's a quite recent organization which was founded 5 years ago, and we have got now 25 people who work on communication on different areas. And I give you a short overview about the why isn't it doing it what I'm supposed to do? Okay, here we are. Yeah, about what we did in the ETEKINA project. So I'm just going to share now my screen, and oh, here we are. Finally. Okay, sorry about that. Right, the importance of communication. So basically, what we usually do, we think about a communication strategy, and the strategy really has 3 elements. We first of all look at the actual, what are we planning to do? What is the actual strategy in terms of who we're trying to reach? What is our target groups, target audience, and how we can reach them? What kind of communication channels are they on? How can we find them, and with what kind of means? What kind of, do we need to create a brochure? Do we need to find them online, and on which channels, and so on? We also have to think about the key messages. I mean, today we learned a lot about, return of investment, for example, which is a key message, obviously, for people from the industry. So this is definitely one of the key messages you need to bring across. And it's also timing, because there's no point of talking about return of investment when you really haven't verified it at a certain stage, in time. So this is also something quite critical. And once we thought about the strategy, then we have to go into action. We have to produce materials. We have to produce articles, videos, social media posts. I mentioned the brochures. We have a website that we update continuously. But then you still don't know, is this all working? So we have to also evaluate it. So you have to see, well, what happened to our publications? Are they being read? Are they being published? Are they being, the videos, do they make it into the television world? How are our social media going? Are these, are they being seen, and do we have enough visitors on our website? So this is all working. And if it's not working, or if it's working extremely well, then we may have to adjust it if necessary, and then maybe adjust the strategy again, and so it kind of becomes a little circle. Now, this is the whole communication background on the strategy, but similar to that, we also have there's also the dissemination, and dissemination is a kind of a term the EU loves, and it's basically, it means that you communicate yourself, that you show what have you achieved. You publish that perhaps in a scientific journal or in a conference, and so here again we have the 3 elements. We have got the strategy part, the action part, and the relation part. So you have to decide on the topic you want to produce your scientific paper on, for example. You publish it, and then you measure it in terms of your citation and impact factor, and both the communication and dissemination, if you see them as a parallel, way how to move on, then you will create the impact. But I'm going to focus now on the communication side, and we really have and I mean the first and most important question is always, who are you trying to target? And we kind of identify 3 main targets. So let's call them the experts are the first ones. These are the engineers, the researchers, probably the people who are in here who perhaps have read, the scientific papers already, who are really into the subject and know exactly, the subject. So these are the key people who know pretty much the details of this technology and understand it quite quickly. Then you have kind of the semi-experts, the people who have to apply the technology, the energy managers, perhaps of another industry who is interested in that kind of savings we heard about today, or an industry association. It could be policymakers who are interested in, how could they kind of support this kind of technology in the future. It could be research or students who really, look for interesting path of their career, and they could be interested in it. So they have a certain background, but they're not real experts yet. And then you have the lay persons, the people who think, oh well, this actually sounds quite interesting, but really don't understand much about the need of the industry or the technology itself. So these are citizens or most journalists. I wouldn't say all journalists, but most journalists who haven't got that background information. So if we look at the target groups, what we do with them? Well, basically, they have this kind of obligation to know. They really should know about this thing. They need to understand the scientific papers and read them. So we, as the communication partner, we need to guide them. We have to make sure that they find these papers. And so what we're doing there is that we promote the conference papers or the conferences or the scientific papers. And we do this mainly with the, where we provide the links to the scientific papers and conferences on social media. This is the key area where we are involved in ResearchGate, LinkedIn, and Twitter. So just to give you an example, I mean, you're probably aware of ResearchGate. There we can basically upload the entire papers. People can connect with the authors, and it's a kind of interesting tool to provide all the information that we have on the scientific findings. LinkedIn is also very interesting, but this is where we can kind of already provide a kind of a summary, almost like an abstract, where we can provide that in detail, and then already link to the scientific papers. And last but not least is Twitter. And Twitter is actually quite interesting. Although we hardly can put in there any or much information on this, it has shown that if you as a researcher tweet about your project, the likelihood to get read, to get cited is much, much higher than if you don't do that. The figures kind of vary. It could be something like double to even more than that if you actually tweet about your research. So these are our expert groups. Then, as I'm called, the semi-experts. So these, for them, it's really important. They really should know more about our project. So the energy managers, industry associations, the policymakers, researchers, and students. So they have a strong interest in the topic, but they will perhaps not read these scientific papers because they're a bit too technical and perhaps go too much into detail. So they need some sort of simplification, which provides them with a good understanding of the key results. So for them, it's quite useful that they get their hands on a brochure, on articles, maybe on a promotional video. So that again is our social media, the website, and also trade magazines. I mean, you're probably all aware of these trade magazines in your office that you reach, and in there you will also find possibly some articles about the ETEKINA project. And I give you some examples what we've produced and explain you why we did this. So we created an infographic. There was a particular bookmark. I also have one here. I don't know if you can see it on my camera as well. So this is a bookmark that we created. And here you just see the GIF of it. And so if you move around it, then it changes the color. And why did we do this? Because it doesn't really inform a lot about the project, but it kind of it raises awareness. So this was the actual objective, to raise awareness about the project, and we did this very early on, within the first year or so. And and we had to even reprint it because people loved it so much that we did reprint. And that one kind of explains the heat pipe concept. A very, very important part of our work was working with articles, interviews. That was to raise awareness, obviously, but also to inform. So this is already going a step further. And we've created, this is a typical trade magazine article that we wrote and we published in the Heat Exchanger World, for example. But there have been also online publications, different ones. Our Slovenian partners have very good contacts with the local press there, so they have been featured quite on a regular basis in the news there. And you can see all these graphics you see here. These were produced by us, and they're being reprinted, reused over and over again in different publications. So this is very good. And here is again another long article or interview that was with Professor Jouhara on in the heat exchanger world. Also, the final brochure or brochures in general are very important to as promotional materials to inform the stakeholders. This one has been printed just it was just arrived last week. I have it here in front of me. We have got stacks of here in the office, and hopefully we'll bring this to one of our next conferences because we will still inform and talk about ETEKINA even though the project will be finished. So we will share that one, and it's also online already, the PDF version, so you can have a look. And in there we have we have summaries of what we're doing, and for each demo case we explain a bit further what has been done and what was the context of it. We also produced a final video. The final video is basically ready. It is there to inform stakeholders. It's a 12-minute video, and that kind of explains the whole each demo case again in more detail. And we have all our main actors, the ones you've heard today, and many more who give their statements and explain the heat exchangers, and we have animations, so we can explain it in much detail how the heat pipe heat exchangers are working. But there's also a third group that we should not really forget. These are laypersons, people who are curious to know, so the citizens as journalists, but don't really have this background, on heat recovery or waste heat recovery. So they usually have an interest, but this is mainly to solve societal challenges. So for example, how to become carbon neutral by 2050, but they don't have this technical understanding of the solutions. So here we produce mainly journalistic materials. We produce the video news release, we produce journalistic articles, interviews, press releases, animations, and so on. Our main channels are TV stations, tech magazines, and so on, social media websites, and so on. And actually, we will share with you in a minute, or Corinna can share that in the chat, a video that we've just produced for journalists. It's also being released today. And let's see, how successful we are if we will manage to get this on television. I think I'm very confident at the moment because we already had some interesting discussion with journalists who want to publish it. So yes, so this will be a way to really, make this known to a very large audience beyond this group where we are here at this conference. And this video news release, as I just mentioned, it's aiming at science and business journalists and we provide them basically with TV footage so they can adapt it for their own channels. We've created all sorts of different distribution channels. So we have a satellite fee that goes via the European Broadcasting Union, which is basically an association of all public broadcasters. So in England it's the BBC, in Italy it's RAI, and in Germany it's ARD and ZDF, for example. And we have a direct network of journalists that we provide our materials to, and we have our own web portal, Free Footage, where we provide this material for free for the journalists, so they can download it and adapt their own story, and we provide all our context as well, so that they can, whenever they've got questions, they can come back to us. Now, I also just quickly mentioned this evaluation part. So we need to then evaluate, how successful we were with all these things, with the publication, with the TLB reports, with our social media and website, to understand our impact. Because this is a really key thing. I mean, we really want to create impact, and what will be this long-term impact of these actions. And this is we don't know yet at this stage. I mean, we're very confident that it will be good, and we try to have our contribution to that. So basically what we've done, we've created suitable marketing material using some of the unique selling points, which is like this really low return of investment, and that's a high return of investment, sorry. And this, how passive it is, and that it works really well. That we have created this awareness and understanding by research and industry, that we also have created an awareness by the public and politics. And we already received quite a number of concrete inquiries via our website on this technology, people who are interested in this technology, that we then forward on to our technology partners. And we also hope that we have managed to gain some interest from students in this research. And if you want to summarize what have we managed here, I think, ETEKINA is a special interest project. We have to say this. It's not a mass media thing where we say, well, we're gonna save the world here, but we obviously have an important role. So our main target groups, because it is such a special interest on energy-intensive industries, these are the experts and the CM experts. That also means that the quality of targeted outreach is more important than quantity. So if we only have 200-300 followers in our social media, well, that perhaps is not so critical than having 10,000, because it's those 200-300 that are more important, or that are important. That we have created a comprehensive dissemination kit with the brochures, videos, all these video materials that can be used now in the future for the marketing activities, and that we also will make sure that the visibility of ETEKINA will continue after the project has entered. And that basically means that tailored communication is essential for to make sure that the legacy of the project is successful. And this is, I think, my main message I want to bring across here on communication side. And that's it. I don't know if there are any questions. Yes, as I said, in the chat there is the video news release and also the final brochure that Corinna, my colleague Corinna, posted. So good. I think if there are no questions, then we can move on to Jogita. Jogita Malinowskati. Awesome. Maybe you say that better. It's one of those more difficult words, I think, names in our consortium.
Thank you, Elmar. Good afternoon, everyone. Give me a minute to share my screen. Probably will need some help. That's not. See. Can you see it?
Yes, now we can see it.
Okay, let me try from the beginning.
It's not in presentation mode yet, but we can see it.
It should be now. Oops, sorry. It should be in the presentation mode. Is it not, Elmar? No.
No, we see it like
If you click on F5, Gita, perhaps F5.
Okay, let me see. Because I can see at my laptop, it is in a presentation mode, so that's why. Okay. I assume that, we don't have much time, so maybe as long as you can see the slides, we can continue.
Okay.
Is that okay?
Yeah.
Thank you for the introduction, Elmar. Yes, I am Jurgita Malinauskaite, and I have probably the most difficult name. I guess Lithuanians, we do have with names, and I sometimes joke with my students that if we can't spell my name correctly, we can't pass the exam. So be it. I am truly delighted to be part of this project and presenting at this final conference. I think it is quite unusual that, in such a technical project, you have some lawyers involved or researchers from law studies. So I'm a professor at the law school, and I'm really pleased to be part of it because to be honest, all the changes that we are implemented and we are driven by policies. And today in my presentation, how new policies facilitate heat recovery system in Europe, I'll be looking at the European policies mainly, although in this project we also looked at national policies. And about that a little bit later. Now in terms of the current status quo, the EU and the member states, we do need to pick up the pace on energy savings, as the next 10 years will be decisive in reaching the Paris Agreement object of 1.5, requiring unprecedented scale of action in all sectors. And as you remember, COP26 in Glasgow last year, so it was really big stress added on climate change. So at the moment, if you look at energy use, accounts for 75% of the EU's emissions. So therefore, we need really to look at EU policies that should set the pace with strong and binding targets and measures, ensuring a level playing field. And implementation of transformational measures at the national level can drive the reduction of energy consumption. And obviously, it's not only about benefits going of greenhouse gas emission, but also creating green jobs, lower energy bills, and most obviously improved health. Now, what is good to celebrate that industry actually, how addressed by the European Commission, is one of the sectors that has already achieved significant energy improvements over the last decade. However, we do admit in most recent policies that the amount of heat produced from industrial processes and wasted in the EU, it is estimated to be enough to cover the EU's entire heating needs in buildings. So the message is clear that this heat recovery is not reaching its full potential in Europe.
Jurgita, if I may just, the presentation doesn't seem to move. If you want, I can present your thing and you just say when I have to move on, because we can't see it moving on. Now it's something that's moved on.
Okay, if I do this way, I know it's not in a presentation mode, but Can you see now?
Yeah, we can see now the 4 arrows in orange.
I think, Elmar, I think it might be easier if you do it from your end and give your Gita the control so she can just click on the screen.
Okay, shall I stop sharing then? Sorry about that.
I don't know if that works.
Okay.
I think no, you just have to say when you just say next slide, and then I can do it.
Yeah.
Yeah.
Okay, so would you like me to stop sharing then?
I'm sharing now.
Oh, okay, I can't see. Let me go back. Okay. Yeah, we can move to the next slide, please. Okay, so here. Let's talk about EU strategies and packages. So as you can see here, the first one, EU strategy on heating and cooling. In 2016, what the EU did, the Commission launched this strategy, and it's now nearly, it is 6 years ago because it was launched on 16th of February 2016. So in here, what the Commission looked at, tried to include plans to boost the energy efficiency of buildings, improve linkage between electricity systems and district heating system, and also increase the use of renewable energy and encourage reuse of waste heat generated by industry. And that is the very first time when the Commission looked properly at the European level, because as you look before that, all the heating and cooling was more to do for national. So national member states, it was in their policies to do something at this point. Now, moving to how, from legislative point of view, so strategies, it's good, it drives, it shows the future, but we need more measures, more compulsory measures from the member states. So what the Commission published is the so-called the clean energy for European package. And in this package, what we did, we looked at the directives. We revised the directives, and Energy Efficiency Directive, it's the most relevant for our project. So we looked the most of it. And obviously it is the directive also drives the main principle in Energy Union, EU Energy Union, so-called the energy efficiency first. And I'll get back on the next slide in terms of specific measures that the directive, Energy Efficiency Directive introduced. Now, what we have right now, as you can see, the most recent one is 2021 Green Deal and the recent package, Fit for 55 package. And here again, showing how the Commission actually reviewing legislation. Once again, even though we have Renewable Energy Directive, we have Energy Efficiency Directive that been just revised back in 2018. So we are looking this year, we have a new proposal for new revisions. And most likely we will have new law by the end of this year. So again, showing really how the Commission is looking to achieve that sustainability. Now, in terms, maybe we can move to the next slide. In terms of the targets, so we have a EU baseline. So as I said, very first Energy Efficiency Directive 2012 that set the target of 20 to achieve energy efficiency of 20 by 2020. Then we have a revision in 2018. You can see the target has increased 32.5, even though through the legislation process it was actually proposed even higher, but member states did not agree. And now looking at the Green Deal and that was Fit for 55 package, they discovered that actually, you know, if we're looking at achieving to have zero carbon emission in EU by 2050, these targets are not sufficient. So the proposal is, you can see, is 36 and 39 for primary and final energy targets, final and primary energy consumption. Maybe we can move to the next slide, please. Now, more specifically about this one target. Here, as I said, especially I think that COP26 has helped because the Commission initially had this 40% target, but it was increased to 55 by 2030. It's just because we realized that, you know, to achieve climate neutral economies by 2050 will be unlikely. Now, that's why the targets had to be revised. One thing that obviously of energy consumption, what the Commission admitted, because it asked member states to submit their plans, and we noticed that there is a gap that we want to achieve energy efficiency by 2030. So that's why one of the reasons was revised, and also energy consumption was a bit difficult to assess because of COVID impact. So now in terms of proposals, I would like to make it clear that this sort of what I put on the slides, they are proposals, so it's not final, but most likely or close to that number, it will be accepted at the EU level. And obviously it will be another 2 years when member states will have to implement it at national level. So what is new, as you can see, targets for energy efficiency has increased. Then we have also a binding target for renewables to 40. Initial percentage was 32. So if you look right now at Renewable Energy Directive, it is 32. Now the proposal is to increase to 40 by 2030. We also have the industrial sector that has some targets for the very first time. So here it is for the industrial sector is to increase its renewable share by at least an indicative 1.1 annual average percentage point. Also, it will be target 50% of hydro use in industry is to come from renewable sources by 2030. We also have, in terms of heating and cooling sector, we also have some targets. The indicative target of increasing the share of renewables by 1.3 per year is replaced by a binding annual target of 1.1, which member states we can combine with individual increases, sort of between 0.6 and 2.9. And in terms of member states using waste heat and cooling, the mandatory increase shall be as high as 1.5, and previously was indicative 1.3. So once again, as you can see, targets are becoming more increasing, and in case member states they use waste heat and cooling, they may be counted as up to 40% of the annual increase. So it is a combination of waste heat and a combination of renewable that it is proposed. And if you may move to the next slide. Sorry, Elmar, to the next slide. I don't know if it is frozen. Or...
We are now further opportunities.
Yeah, I'm just getting close to the end. Okay, so for the opportunities for the industries to have direct feed via district heating systems. So any heat waste recoveries can feed for these district heating systems. And there are some examples right now in Sweden we do from industries, from factories, we can heat houses in surrounding areas. What is important, obviously, to build infrastructure. So infrastructure development is quite important because member states, obviously, we need to have their local policies. We need to make it feasible. Because now it is a cost-benefit analysis. It is very important to make it work. We do have right now some new proposals as well to assess that economic feasibility of increasing energy efficiency of heat and cooling supply. That member states, what we need to visit is sort of to ensure that we do have this cost-benefit analysis. For example, if we have an industrial installation with an average annual total energy input exceeding 5 megawatts in order to use utilization of the waste heat on-site or off-site. So in terms of energy audits, I have not seen any major changes in terms of that. So because at the moment we have compulsory energy audits every 4 years. In terms of small and medium enterprises, we are recommended these energy audits, but it's actually to look at more as not some sort of burden, but it should be looked at as an opportunity for businesses to improve. And just final point, the recent surveys done by the Commission, because we have to do it as part of review of legislation. What was interesting that regarding industries, the survey showed that the key barrier is likely to be that most businesses do not have the expertise to know what technical energy savings opportunities are available and what their economic benefits might be for the business or for the industry. So as you can see, I totally agree, communication is the key here. Thank you. Next slide, I think it just say thank you and my email. And I added a few publications as well that was more from regulatory side, more from national policies in Slovenia, Spain, the UK and Italy. Thank you.
Okay, thank you.
Do we have any questions?
Sam is there with the question.
Thank you very much, Agita. Thank you. And yes, we have to behave. We had the lawyer in our consortium. We still have a lawyer in the consortium. So you can imagine that everything we say has to be very, very well, balanced. So, but your support was tremendous. Thank you so much, Agita. The question now is, I mean, we have in this project, I can't say we're lucky, but we have gone through a cheap gas as a fuel at the beginning of the project, a really expensive gas now. And if you look at the gas prices as an index between the beginning of the project and the end of it, you can see a really big change on the upward for the gas prices. Also, if you look at the carbon emissions cost, look at the 57 euro figure we have right now. So lots of change changed from the beginning of the project to the end of the project, which I believe is strengthen what you have been trying to do with influencing the policymakers on implementing technologies such as the one we have in ETEKINA. How do you see the way forward with regards to this implementation? Do you see us, for example, contributing as a consortium to a white paper? Do you see us doing things on behalf of the consortium toward the Commission to raise the awareness of this? What are your thoughts?
Thank you, Sam. It is a very good question. It's true because you see policies, they need to be influenced, they need to be inspired by some examples. And I believe ETEKINA really shows an excellent example here. And it would be very good to evaluate let's say, you know, after installation, 5 years, 10 years after, what sort of improvements we see and what cost savings we can see. But I already see, you know, really positive examples from the industry that, you know, we can really save energy. Now, in terms of, you know, future, it's like zero fossil fuel. That's the vision. But, you know, the EU now clearly shows combination of using waste heat and renewables. So it will be combined, and it is phasing out actually now in law, because if the Renewable Energy Directive proposal, I believe it's about 450-page document, so it's lots of reading. So they are phasing out, they're really showing how, you know, member states will have to achieve percentage-wise in terms of waste heat, percentage-wise renewable, to make sure that it is zero by 2050. And, you know, we will see. I think it would be quite useful to look to revisit our project in a couple of years and present to the Commission actually how we implemented things in practice. So, yeah, definitely. Thank you.
Thank you very much. Thank you.
I can see some comments in terms of funding. Yes, it's not that businesses, they are left without funding. The problem is that member states, obviously, we must comply with state aid rules. But we did look at some funds, and it seems that member states, the EU has in mind that actually they will have to support businesses. They will have to support industries because technology is not cheap. And there are some funds available, but as I said, we have to comply with, if we are talking about EU, we have to comply with EU state rules.
Good. Thank you, Peter.
Thank you.
Thank you, Charles, for your question. I think
it was about funding. 1 second, I can see. Is there something else? New technologies. 1 second.
No, he just says new technologies often need a push as well as a pull from those who understand the potential to mitigate perceived risks. Yes.
Oh, I do understand, and the investors, obviously, you know, they have that risk as well to invest in new technologies. So yes, I totally agree. I think it is what the EU is looking at, this combination of private and public funding agreements.
Well, I mean, then that's, you know, this is kind of the future. Let's continue with the future or the legacy of ETEKINA, because we identified definitely one result that came out of the ETEKINA project, and that is the iWAYS project. And we have here with us Luca Montosi from the University of Modena and Reggio Emilia with us.
Yes.
Who is
Elmar, I don't know if Sam had so.
Oh.
Okay, so
thank you. Look, I just wanted to follow up actually from just in answering Charles' question, if I may, very quickly. I mean, the ETEKINA project didn't come from very low TRL; it came from intermediate TRL and all the way up. And in order for this new technology to be implemented, we had to demonstrate the business case. And this business case is basically what is acceptable by the industry. So whatever we do, we need to also look at the venues where funding is available for which TRL, and also to be acceptable by the end user. In our case, we were aiming at the golden ROI figure of 24 months or below. Thank you.
Okay, Luca.
Thank you.
The floor is yours.
Sam. Okay, I'm going to share my screen. Can you see it?
Perfect.
Okay, so thank you, Elmar, and good morning, everyone. So what's next after ETEKINA? We heard a lot of great results from the ETEKINA project. We heard the demo cases describing the results they achieved by implementing the ETEKINA technology. But also listening to the demo cases description, I think that one of the main design criteria of ETEKINA was clear. So we tried to avoid low temperature in the exhaust. We tried to avoid condensing acid in the exhaust gases. So after ETEKINA, we tried to go beyond this limit. So with the iWAYS project, one of the main challenge we are facing is to recover the heat from the exhaust gases by lowering the temperature of the exhaust gases below the dew point of the water content in the exhaust stream. That means that we are not only condensing a part of the water content in the exhaust gases, but we are going also to condense acids that might be present in the exhaust gases composition. So this is a big challenge for what's come next ETEKINA. By going below the dew point of the water content of the exhaust gases, we are also going to recover the water. So by condensing the water, we can recover it, we can treat it, and we can reuse it in the industrial process. So we can decrease the water consumption of the industrial process. Along with the water, we are also condensing other substances, but some of these substances are indeed a product for some industry. So another target of the iWAYS project is to recover the material in the exhaust gases. So this is the concept and the methodology for the iWAYS project. So we are addressing a waste gases stream, and we are going to recover heat by this stream, and we are also going to recover the water by condensing the water vapor in the gaseous stream, and we are also going to recover the materials in the gaseous stream. And we are going to use heat, water, and the materials in the industrial process we are addressing. So what's new in this approach? Indeed, there is a lot of new technologies because the heat pipe heat exchanger has to face a corrosive environment, so it must stand corrosive acids or other substances that might be present in the exhaust gases. Also, particulate load will be an issue, and we need to recover both water and material and to use them back in the industrial process we are addressing. Or, for example, in some cases, if what we are recovering is indeed a product for this industry, it will be a commodity that can be sold by the industry itself. These are the numbers of iWAYS. So we are 19 partners from 9 countries. We have 3 demo cases, 4 technology providers, and the project will last 14 months. Indeed, 1 year already went through. So we are in the second year of this project. These are the partners of the consortium. I'm sure that you can recognize some of them. Some of them are also in the ETEKINA project. These are the specific objectives of the iWAYS project. And just to mention a few figures of the iWAYS project, we are aiming at reducing by 30% the freshwater consumption of the industrial process we are addressing. We are going to recover 20% of the heat from the exhaust stream for that industrial process, and the payback is also an important topic for the iWAYS project as well as for the ETEKINA project, and we are aiming at a lower at a payback period lower than 5 years. Indeed, we have also other specific objectives, because we are going also to implement a monitoring system in order to increase the control and the monitoring capabilities of the industrial process. And we are also going to develop the SS tool for the evaluation of possible alternatives to fresh water for the industrial process. These are the technology components for the iWAYS project. We know very well the heat pipe based heat exchanger, but as I said, we are aiming at condensing the water content of the gaseous stream, so it will be a heat pipe condensing economizer, because we are indeed condensing water and eventually other substances in the gaseous streams. We are going to develop a decision support system based on sensors and control systems that will be implemented in the demo cases. And water treatment. Water treatment will be another important topic for the iWAYS project, because, as I said, the condensate will be treated and purified to the level required for the industrial process, so that we can reuse the condensate in the industrial process itself. A very quick description of these technologies. This is the heat pipe heat exchanger. I'm not going into the details about it. We heard about the functioning of this technology. And as I said, the step forward for the iWAYS project will be decreasing the temperature of the exhaust gases below the dew point of the water contact, but eventually of sulfuric acids or other acids that might be in the exhaust stream. The decision support system will be another technology developed within the iWAYS project. So a 3D visualization and data analytics, integration and forecasting and decision making in real time, and a flexible monitoring process, control and optimization dashboard supporting an end-to-end process of data collection, harmonization, processing and visualization. Then water treatments. Indeed, we are working on different water treatments. We have different demo cases. We have different industries within the project. In a minute, I will show the demo cases. So the requirements of the water treatment will be different from demo case to demo case. So we are involving different water treatment. Some of them have a quite low TRL. such as the photocatalytic nanofiltration system that will be developed within the iWAYS project, but we are also using membrane distillation, ultrafiltration, and reverse osmosis, and also evaporation and crystallization treatment. Indeed, these treatments have an higher TRL, but they will be implemented in an industrial sector where currently they are not used. So iWAYS will be a possibility to discover new implementation, new applications for these water treatments. This is the photocatalytic nanofiltration reactor. I'm not going to go into the details of this treatment, and this is an example of an assembly of a water treatment system based on the previously mentioned technologies. Now, I'm spending a few words about the demo cases. We have three industrial sectors: ceramic, chemical, and steel sectors will be involved in the iWAYS project. The ceramic industry in the project is ceramic Atlas Concorde, so we know them very well, and we are going to implement the iWAYS technology in one of their facility. The chemical industry is Aluflor AB in Sweden, and they are producing aluminium fluoride. That means their exhaust stream is extremely corrosive. They have acid in it, and this is a very challenging demo case in terms of corrosion resistance for the heat pipe condensing economizer, and also for the water treatment system that should separate the acid content from the water content. So the first one can be sold as a commodity for the industry, and the water can be recycled back into the industrial process. The third demo side is the steel industry, Tubasex. They are producing steel tubes, and we are going to address the cooling process for the hot tubes. So we are going to recover heat and water from this process, and the heat will be used in the water treatment system in order to enhance the overall water treatment system of the industry. So this is what comes next after ETEKINA. Here you can find our social media. So if you have any question, please contact us, and thank you very much for your kind attention.
Great, thank you very much, Luca, on this outlook of what's going to happen next in some other energy-intensive industries, and how you're going to recover energy and water. Very good. Right, we're running slightly out of time, but we'd really like to have a short, discussion with Professor Jouhara and everyone else here about, is this the way forward to reach the 2050 goals for the energy-intensive industries? Because this is an amazing challenge, as we all know. And somebody mentioned this. Was it Jogita, I think, mentioned it. It's she sees it as a way to, the combination of waste heat recovery together with renewables perhaps could be really, or is going to be the way forward. Sam, where do you see, now going back to the ETEKINA project, where do you see the ETEKINA project in this long-term goal?
Thank you, Elmar. It's a very valid question, and I'm glad it came after Luca's presentation. Like you saw from Luca's presentation, basically halfway through ETEKINA, we identified that there is a potential for better, more energy efficient process if we are to go down the route of, say, going below the dew points. For example, in various European countries, you can't cool the exhaust after the waste heat recovery system below 150 degrees. And this relates to basically protecting the stack from corrosion, etc. So by having thought of this and came up with the idea, which actually was used to create the iWAYS consortium, which is now in this second year, as Luca said, we now are in that domain where we are hoping that the exhaust after iWAYS will be, it might be just too ambitious, safe to breathe, because all the corrosive elements would have been condensed, and some of the water, if not most of it, will be condensed also.
Sam, you've just muted yourself.
Sorry, yeah, oxygen, nitrogen, and some water vapor. Now, what does that take, and where does that take us beyond? Let's say beyond iWAYS. I mean, iWAYS now is a very ambitious project that aims at innovative water technologies, innovative heat pipe heat exchanger technologies, and we are hoping that at the end of it we'll have a really optimized waste heat recovery and water system. The hot topic at the moment is CO2. If you look at all the activities around Europe and globally, really, CO2 is on everyone's lip. Basically, people can't talk enough about it. In the last COP26, there is a very ambitious target that was set by the G7, the G20, and most of the countries that attended the conference. So what I think, from where I stand, the next logical step would be to combine all these innovative technologies, ETEKINA, which is now concluding, iWAYS, which is now picking up, and go toward energy CO2 capture and storage, which I think is the logical move. And we are already actually in discussions with a few partners, and there are some projects ongoing. But what I'm thinking about is actually implementing the technologies that we have developed in ETEKINA, and we are developing in iWAYS as part of pre-treatment for the exhaust before the carbon capture. Because that seems to me the logical step, and I'm just throwing this question in the air. And if anyone would like to comment on this, and if you agree with it, or if you think there are other ways that we should be thinking. Any thoughts from any participants? Any thoughts on this? Do you agree, disagree? Do you think we should be going a different way?
Hello, Sam. I agree completely. I agree completely with you, because we are trying to find out any system to capture the carbon dioxide, and the limitation is the other component that could be in the exhaust gases. So first step is to eliminate these acids or any other element, particulates or whatever, prior to carbon capture system, carbon capture system. So I completely agree with you. Thanks.
Thank you. Charles?
Thank you, Sam. Yes, I take your point, absolutely. But I suspect that so many carbon dioxide emissions are fugitive. They are from small sources that are dispersed everywhere. And the practicality of carbon capture and storage for the majority of CO2 emissions is going to be very difficult. Where they're concentrated around big power stations, yes, I think that's absolutely the case. I suspect, however, that if the hydrogen economy ever takes off, then in fact we won't have that problem of fugitive emissions, because the small sources will be powered by hydrogen, and maybe the major ones still by natural gas with your carbon capture and storage. But I think we may find ourselves with two different energy supply economies, one for the smalls and one for the large.
That's a good point, Charles. But can I just go back a little bit just to make things clear? We are focusing on energy-intensive industries here, and these are industries that adding the carbon capture element to them actually will give them direct saving with regards to their emissions. I totally agree with you regarding the small emitters of CO2. That would be very complex. And I know the hydrogen economy now is picking up, and there are few basically routes to which economy or energy economy we're going towards. But I just want to reiterate, we are here talking about energy intensive industries, and this is basically what we think is the way forward.
But if I can add a question here on this, I mean, as I understand, the hydrogen pathway doesn't really exclude waste heat recovery, does it? Because
it has to be part of it. It has to be part of it.
So that's the other route, isn't it? That you would combine those.
It's a very valid point. The hydrogen is now picking up, and thank you, Charles, for raising this point. What we have to understand here, we are assisting technology, not the technology. So with our systems, with either ETEKINA or the iWAYS or any assisting systems, we are the pre-treatment of the stream that will then go to either the hydrogen plant or the CO2 capture, depending on which application you're going for. Because there are people who are actually thinking of hydrogen from water and using various sources and some very, very innovative technologies there. We are in ETEKINA or iWAYS. Now we mentioned iWAYS. We are actually aiming at the pre-treatment of the exhaust fumes and trying in iWAYS to clean them so they can be easily handled by the CO2 capture afterwards. And CO2 capture and storage, that's a different technology that we're not dealing with here, but we can make that process much simpler.
In fact, I think there are like two big routes in order to get carbon neutrality in energy-intensive industries. One is trying to avoid or to minimize CO2 emissions, and then you have different strategies like energy efficiency in order to consume less, or waste heat recovery also in order to consume less, substituting natural gas, for example, for hydrogen as fuel. So I mean, there are some routes in order to minimize the consumption, and then there are some other routes in order to, once you have optimized your consumption, trying to be as neutral as possible, like, for example, by capturing the CO2 emissions. So I think these two routes need to be set at in parallel, trying to minimize CO2 emissions, and then some other strategies to avoid CO2 emissions like electrification or hydrogen and so on.
Yep, thank you, Nerea. Valid point. Any other comments?
I just have another question that kind of Luca Manzini, I think, was mentioning on the certification, because I was just wondering, now you had to go through this whole certification process, and as I understand, this was quite a challenge. But how do you see this now, in terms of the legacy? Was this maybe now as an advantage, perhaps, for the future, installations that there hopefully will be?
Yes, of course. I mean, it was some kind of new area of investigation for us too. Okay, so of course it was also some sort of learning by doing, and I think it's quite honest but unavoidable to admit that if I had to do it again from the start, some things were made differently now. Okay, in order to get a smoother approach also from this perspective. But yes, it was a very long, let's say, path, a long road, but which brought also all in our company a greatest knowledge, a bigger knowledge of certain regulatory issues that had not been properly addressed up to now, especially concerning the PED and the let's say, danger of having superheated water running inside. I mean, it was something that it's not common in our sector. Maybe common is not even the right word. I think it's unique. It's I think it's the only installation as such in the ceramic sector, and probably you cannot even find many of them in Italy as well, in the whole industrial sector.
Can I just add to that, Luca? I mean, the challenge for us in ETEKINA was a big one. In fact, it was at one point it was a rather crucial challenge dealing with two certification bodies, one in the UK and one in Italy. We were lucky at the time before the deadline for the Brexit team, so working like one team. But then after Brexit, we had two different rules, but I think they come from the same source anyway. So having gone through this in both unified approach and the two approaches afterwards, I think we learned, I'm sure Luca would agree with me, we learned something new here. We learned how to get the certification done proper, that is compatible between a UK partner and European partner, part of the EU, for example, and that is now will help us a lot moving forward, because I can say with certainty, I have never seen the CE marking on a heat pipe heat exchanger before. Now we can. And heat pipes in general, they follow something called sound engineering practice rules because of the diameters involved. But now we have the shell and the ETEKINA unit, for example, and demonstrate at such a high pressure, we had to go and get the certification approved. And now we have the CE marking. So that was an achievement in its own right. So yeah, I totally agree.
Let me add one more thing. Okay, it was not a technical challenge, not a regulatory challenge, but there was one more thing that we always forget. We were delivered the unit in 2021, last year, and Brexit already happened. So we had to receive the unit, and to deal with that with customs, it was not, it was quite tricky. Okay, our administrative offices were getting mad at that because you know, the year before it was quite a smooth delivery. Okay, there was no barrier. Also to deal with that, it became quite important. Okay, but we managed so okay this way.
We certainly did. We certainly did. I remember. Yeah, absolutely.
Now, what does that mean now to the, I mean, now we have, potential or people who could be interested in this technology, and they want to, verify how they can install it in their paper factory or in their other, chemical factory or wherever. What is the best way to find out about this? Maybe Sam, you can, what if somebody wants to look, have something like an ETEKINA installation.
I mean, we are now at the required TRL level for the industries involved, but also we can explore other industries. What we need really is the set of thermal data that we are dealing with and the nature of the exhaust streams, and also what is the end use of the heat. And based on that, we work very closely with the Econotherm that manufacture these systems, and basically we can support the industry with regards to developing the PNIDs, the installations, the economics, and etc. So I think we are at that level now as a consortium to provide that. In addition, something we don't shout about much, but it is a huge achievement that we have developed modeling tools for the 3 demo cases by the involved RTDs. For example, working with the University of Modena, we worked on the CFD side where we can now utilize CFD, which is a very complex modeling practice to get to understand how we can keep those particles suspended in the air. And this process hasn't stopped. It will continue. We have very active collaboration with Modena on this. And in addition, for example, working with Joseph Stefan Institute, we are doing modeling work using a tool they have developed on the process itself. And that model is helping us to replicate this. For example, if Ravne is to decide to go for other sites, then we can perhaps help them and get the model to give them an idea about what they expect. And that will help their decision makers to kind of make a decision on this or not. Working with IKERLAN, for example, working with Fagor, working with Insertec, working with partners in Spain who also, for example, IKERLAN, they have developed, we got involved in that too, a tool, and this tool is also providing quite useful modeling for the process. So having the RTDs involved, having all these modeling tools being established, and also using complex modeling techniques, all of these can be used to support complex scenarios. So I wouldn't discourage anyone with complex scenario to come forward, because we have the tools now and we have the capabilities that have been validated in the project that we can utilize and maybe can take the idea forward. And this can be in direct support of the company, or if the challenge is innovative, new, then perhaps we can explore venues of funding to get that done.
Very good. I mean, when I did my interviews with all of you, and especially the end users, I always had the feeling that there's definitely an interest by them to install more of these heat pipe heat exchangers in their other plants and so on. So, you know, these are the last 3 heat pipe heat exchangers we see in energy-intensive industry. That's for sure. But obviously, it would be good to see this also as a, you know, a long and widespread, you know, what's it called? Yeah, that it gets widespread throughout the industries. Good. I don't know if there are any more issues or questions, and if not, maybe I give the word to Nerea Nieto for some closing remarks. Or yes.
Yeah. Well, I think it was a very interesting discussion, and maybe we didn't have enough time to continue, but as you already have said, you can contact us for any issues you may have, for any doubts. If you want to have further details, if we can share them, of course, we will do it happily. So don't hesitate to contact us. You can visit our webpage. You have the contacts there. You have also some dissemination material, all the publications we have done. You can find all the information there. So just to end up with this conference, I want to thank you all for attending the conference. We hope you find it interesting. We are really happy with the results we have obtained in the project. I want to also thank you all the partners, not only for today, but for all the work done during the project. As Elmar also said, we will continue disseminating project results, so hopefully you will continue listening about us and about the ETEKINA project. And yeah, that's it from my side. Thank you very, very much to all of you.
Thank you very much, Nerea. Yes, so yes, please watch the space, follow us on the social media, because there are some more events coming up in the summer, although we are actually officially finishing in on the 31st of March. But there will be more activities on, you know, on the project. You will be able to meet us in person. You will be able to pick up, oh, you don't see this, our brochure here. You can also email me and I can send you one if you want one, or 2 or 3. Well, also thank you very much for all the participants of this conference, and thank you very much for everyone joining here today from all over the world, as I understand. And yes, have a nice afternoon, I would say, and nice rest of the week, and stay safe.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Bye. Bye. Bye.
Bye bye.
No,
Bye bye. Thank you.